So, Andreas, let's just review the question that we're going to try to get answered today. All right. And that question is, what percentage of the Earth's surface is covered by a satellite in the Earth's orbit? Now, you already asked me, you said, Mr. Kramer, hey, what is the altitude of the satellite at point S? And we said, this is a given, this has to be given, that you got a satellite at 22,000 miles above the Earth's surface. You also told me that that line from the satellite to the Earth had to be the shortest distance. And E represents the point or the tangent point at which it is the altitude is the shortest distance. C represents the center of the circle. So what auxiliary line, Andreas, do you have to create now to begin this process, to figure out the coverage? Just take a guess. And you can say the letters of the segment that make a radius. What would that be? Come on, from C to where? Where would you go? Do you have another point already named on this circle? Come on.
CE.
Of course. So CE is a radius. Now, what's another question that you've got to ask me now? Because this is a fixed number. It's a number that we know. And what is that question?
The altitude, what percent of Earth's surface
We already know the altitude is 22,000.
the radius.
Right, the radius.
What's the
So
radius of the Earth?
what is the radius of the Earth? Do you remember? We've talked about this a few times. Do you remember the radius of the Earth? And if you don't remember the radius, do you remember the diameter? And if you don't remember the diameter, do you remember the circumference? Any one of those facts will give you the Earth's radius.
I don't know. I think it's like 60. I think it's like 65,000 the Earth's circumference.
Well, that's interesting. Let's just go to a different page for just a second.
I don't know which one it is. I'm not.
So here's the Earth and the circumference of the Earth. And I want to sort of show you, if I were to look at, let's say we're here in Massachusetts, right? And the United States would be about, oh, and I'm making it up here, but I would say that that's the US. And that this right here is California. Now, from Massachusetts to California is about 3,000 miles. That's the latitude, the east-west distance from the furthest point on the east to the furthest point on the west. So 3,000 miles. So do you think that the Earth's circumference can be 65,000?
No, 65 million I meant.
But now I've told you that this distance, look at the portion of that circumference. And I've told you that that circumference is about 3,000, I'm sorry, that this portion of the circumference, the United States, is about 3,000 miles. So just using your logic, what do you think the circumference would be? And I'll tell it to you in a minute, but I want you to just think about it. If this arc is about 3,000 miles, how many arcs do you think you would create there? About 7? Well, if it's 7, then what would the circumference be?
21,000.
Right. Now, you're very close. You're very close, Andreas. the circumference of the Earth is 25,000 miles. Now, that is an estimate. It's, 24,900 and something miles, but let's call it 25,000 miles. Now, if you're trying to find out the radius of the Earth, and you know that the circumference is 25,000, how can you figure out the radius of the Earth? What can you do? What's the relationship between the circumference and the radius of a circle?
The circumference and radius.
Yeah, what's the relationship between them?
That the radius is 6.28 something times smaller than the circumference.
How did you get that?
Because the diameter times pi equals the circumference, so that means the 2r pi equals.
Oh man, Andreas, you are amazing. That's absolutely correct. Circumference equals diameter times pi. Diameter equals 2r.
Yeah.
And therefore, if we know that the circumference is 25,000, I'm going to write 25K, and we know that that equals 2 pi r, how are you going to find the radius? By doing what to both sides of that equation? Come on, how are you going to solve for r here?
Both sides by 2 pi.
Right. Now go ahead and pick up that calculator of yours. And I want you to divide 25,000 by 2 pi.
Okay.
Are you doing that on your calculator?
I have an online calculator.
Okay, cool. And I'm going to do it on my calculator.
39,269.908.
Yeah, those are just digits. Give me a number that is a very, very good approximate, my friend. What would a very, very good approximate radius be? How many miles?
4,000.
That's right, my friend, 4,000 miles. Therefore, you know the diameter is 8,000 miles. And yes, the radius is 4,000 miles. So let's go back. We now know that the radius of the Earth is 4,000 miles, and we can actually label our segment CE 4,000. Okay, so we've labeled our altitude as 22,000. We've labeled our radius as 4,000. But how are you going to figure out how much of the Earth is covered by this satellite? I mean, what else, what other auxiliary lines do you need to create? Does a satellite just take a picture of one point on the Earth? Or does the satellite cover more than just that point?
More than just that.
Does it cover this part here? Does it cover this part here?
Yes.
Does it cover this part here?
Yes.
What auxiliary line do you need to create? The line has a name. It's a special, say it again.
It's tangent to the.
Yep. Guess what? You have to draw the two tangent lines.
The tangent lines are the.
Now, those tangent lines are the what? They are the what? Come on, they are the furthest point on Earth that has coverage from
Mhm.
that satellite. Does that make sense?
Yeah.
It's the line of sight from point S to point, let's call this point A, and from point S to point B. Now you need 2 more auxiliary lines. And what are those going to look like? Come on, what was the purpose of finding point A and point B? What auxiliary lines can you create to make this happen?
Auxiliary lines you can have to make this happen are
Come on, think about it, Andreas.
BC and AC.
Right, and what
Those
is
are
BC and AC?
4,000
I know, and what are they? They are the what of the Earth?
radius.
They're the radius. And why are those so important? Why is BC and AC so important?
Why are they so important?
I mean, how are we gonna, I mean, what have we created now, Andreas?
A triangle.
What kind of triangles?
Right triangle.
Why are they right triangles? Which angles are right?
CAS.
CAS and
CBS.
why are these right angles? How do you know that those are right angles?
Those are right angles those are right angles because like the tangent is perpendicular to the radius from the point it intersects.
That's right. Andreas,
And they're congruent triangles because of hypotenuse leg.
Ooh, very nice.
The hypotenuse leg means that they're
Yep.
congruent.
So I'm actually going to write that out, Andreas. That's not even a good, correlation. That is a great correlation. The fact that you could see that triangle CBS is congruent to triangle CAS, and you gave me the theorem, which is the HL theorem.
Mm-hmm.
Is there one other that you could give me? Because you know that all radii are congruent, correct? And what else do you know? Come on, what do you know about CS?
CS is
Congruent to what?
CS.
Because of what property?
The reflexive.
Beautiful. Now, that is how you got your HL. But could you have gotten also SSS?
I don't know how you could have gotten SSS. The only other one I see is ASS, which leads to hypotenuse leg.
Right. But my friend, do you see that SA and SB are tangent segments?
Yes.
All tangent segments are congruent.
So you also prove it with SSS.
Right. Now watch
and
this.
SAS.
So watch this. If I draw a random point and make a tangent segment and another tangent segment, I can guarantee you that my tangent segments are congruent. And that's a really cool theorem. A lot of fun. We can go over some other time. But you could have used SSS or HL. But both of them are really, really good. Now, so what? So now you know that they're congruent triangles. I want to know what's the coverage of the Earth. What do you need to know in order to know what the coverage of the Earth is? And I want you to move away from thinking about sides and think more about something else. Come on, triangles have sides and they also have what? Think about this. Let's sort of look at another circle for just a minute. If I know, Andreas, that my circle has a right angle, which is called the central angle. You see that angle is called a central angle? Now that angle is 90 degrees. What is the distance of my arc? What's the degree measurement of arc AB? The measurement of arc AB is how many degrees? Come on, a full circle is how many degrees, my friend? A full circle is how many degrees? So a full circle is how many degrees, Andreas? So a full circle
is 360 degrees.
Therefore, what's the measurement of the arc?
90 degrees.
Absolutely 90 degrees. So you know.
Because it says it right there.
Well, the central angle is 90, but now we know that the arc measurement is 90. And do you understand that the arc measurement is this portion of the circumference?
Yes.
So if my central angle was 90, I would know that my satellite covered 90 divided by 360 degrees, which is what? Come on, 90 over 360, which is what? Which is 1/4, or what percent? What percent, Andreas? Andreas, what percent is a quarter?
25.
Okay, Andreas, if we had a satellite and that satellite was literally right here, Andreas, it was literally right about here, and we drew tangent lines, we would know that this satellite right over here at point S, that satellite covered 25% of the Earth's surface. But does our satellite cover 25%? Or is there another angle we have to be looking at? And if there is another angle, what angle do we need to know? Remember, we found the central angle. So angle ACB is called the central angle. And that central angle tells us also the arc degrees. And that's going to tell us the coverage of the Earth.
Yeah.
So what do you need to know in our problem? Come on, what angle do you need to know? You need to know the measurement of angle what? Here we needed to know the measurement of angle ACB, Andreas, the central angle. What do we need to know here?
We need to know the tangent length.
Well, that may or may not be true, but length is not an angle, is it?
Now
I asked you what angle we
angle
need to know.
BCS, angle ACS.
Ah, tell me about those angles. But what angle would we ultimately need? Do we need just BCS or ACS? Or do we need,
BCA.
we need angle BCA. And that, Andreas, is what you're going to do right now.
Okay.
What do you know about angle BCS and ACS?
They're congruent.
How do you know that?
Kapakaraka.
Right. Because you know, you just proved that these two triangles are congruent. Therefore, all of their corresponding angles are also congruent.
Mm-hmm.
Andreas, how do you find BCS? What have I taught you about right triangles?
Oh, right triangles, the Pythagorean theorem.
Well, yeah, if you use the Pythagorean theorem, you could definitely tell me which side BS was and AS. No problem, because that's a leg of the right triangle, but I don't want to know the side.
What do you want to know?
You tell me. You just told me what we have. We need to know the angle measurements. How are you going to find that angle?
Like them arcs.
Yeah, but come on. I taught you how to find an angle. If you have a right triangle,
Mm-hmm.
and you know, what information do we know right now about our right triangle?
That there's a right triangle. It has a right angle.
Yeah, well, all right triangles have right angles. But what do we know about our right triangle? What do we know about it?
Else do we know?
Well, look, you got to look at it. What do we know? Come on, look at all the information we've written down.
It has 4,000, 26,000 sides.
So we know that one of the legs is what?
4,000.
And
Hypotenuse is 26,000.
that's what we know.
Hmm.
That's what we know. So Andreas, we know that the leg is 4,000. We know that the hypotenuse is 26,000. Andreas, where is the angle you need to find here? If I just draw A, B, and C,
C.
you want angle C? So let's make sure that that's right, Andreas.
No, we want angle A.
Yeah, you want angle A here. Angle A is your theta. Now, how are you going to find the measurement of angle theta here? What did I teach you when you know a hypotenuse and a leg? What can you use?
Median.
No, median's not going to give you an angle. I like the idea of a median, and median goes from a vertex to the what of the opposite side.
Mm-hmm.
The what of the opposite side? Come on, the median goes from a vertex to the what of the opposite side? Come on, what part of the opposite side? Andreas, what part is this? The midpoint. Isn't that the midpoint of the opposite side? And
Yeah.
that's the median. But Andreas, how does that help you? How does that help you find theta? And the answer is that it does not help you. So Andreas, the only way for you to find this angle in a right triangle is to use your trigonometric functions. Do you remember when we did sine, cosine, and tangent?
Oh, yes. Yeah.
Well, that you got to bring that's got to hit you. You know that the only way to find a missing angle, if you have two sides of a triangle, is to use the trig function. What is the acronym that I taught you? Come on, what's the acronym? You got to remember that.
SOTA.
Spell it, please.
COH.
No. SOH. That's the sign. Keep going.
SOHCAH.
Good. Keep
TOA.
going. Okay, now, which one are you going to use? And also close your doors so you don't have that background noise.
Okay, sure. Okay, good.
Okay. Which trigonometric ratio from this angle theta are you going to use?
Cos.
Say again?
Cos.
Okay, cosine. So now tell me a story. Go for it. You can either go directly to the measurement of the angle, or you can first tell me what the cosine of that angle is. You want to do the cosine of the angle first?
Cosine of the angle is 4,000 over 26,000.
And I can write that.
4 out of 26.
Keep going.
Equals 2/13.
Oh, my man. Excellent job. So we know that the cosine of theta is 2/13. Now, we still don't know the angle measurement. How do you find the angle measurement from that information? Come on, what did I teach you that you need to do whenever you're trying to find an angle? The measurement of that angle equals what?
2/13?
Something of 2/13. Something of 2/13.
Cos?
Yeah, but not the cosine. It's the cosine of the angle that equals 2/13. But it is the inverse cosine, my friend. Do you remember the inverse cosine? Do you remember that?
Yes.
Okay, Andreas, then you need to bring that up. When I say to you, how do you find an angle? You say immediately, you need the inverse trigonometric ratios, either the inverse cosine, inverse sine, or inverse tangent. Now, pick up your calculator and tell me what is the inverse cosine of 2/13. And I'll do the same thing on my calculator.
$81.
So you get that this angle is 81 degrees. Is it 81 exactly?
No.
What is it exactly?
81.15.
Okay,
0,
let's
11,
go out.
902.
All right, let's go out to the hundredths. We know that that's 81.15 degrees. Now, let's place that 81.15 degrees.
Yeah.
What's next? Come on, Andreas. If angle SCA is 81.15, then we also know what? Come on, congruent angles. Come on, you can tell me. Andreas, if angle SCA is 81.15, can you tell me about another angle we need? Come on, remember, we need the measurement of BCA.
BCA is 162.3. 162.3.
Yes. And Andreas, that's because angle BCS is also 81.15 degrees. And that's the thing you've got to tell me. Now, how am I going to figure out my percentage covered? What did I do here, Andreas, when I had a central angle of 90 degrees? What did I do? And what are you going to do here? Would you like me to go back to that page we just looked at?
Mm-hmm.
Andreas, we had a central angle of 90 degrees.
Yes.
Gave us a intercepted arc of 90 degrees, which was
162 degrees.
Yeah, but what do we do with that 162?
Divided by 360.
So we take 162 degrees, and it's 162.3 degrees. We divide it by 360. And Andreas, what does that give us? What does that give us, Andreas? You're going to have to do a little math here. You can use your calculator if you like, but you got to do it.
Point 0.45.
And what does that represent?
9/20ths.
Yes, but remember, what was our original question,
45%.
Andreas? Right. So it tells us that a satellite that is 22,000 miles off of the Earth can cover 45% of the Earth's surface. Now, you asked me a really good question at the beginning of our session. You said, hey, Mr. Kramer, how many satellites would it take to cover the Earth's surface?
Then it says, now 2, no, 3.
Yeah, I mean, it's really interesting. I would say 3, but it actually is more than that because there are still gaps. But isn't it interesting, Andreas, that 22,000 mile distance creates almost half of the coverage? Now, Andreas, can you ever be far enough away from the Earth to have 50% coverage?
Yes.
You can. So you think that if we have planet Earth, and I'm going to make it a little smaller here, and we have a satellite way out here,
Mm-hmm.
you're telling me that we can cover 50% of the Earth.
Yeah.
Now you have to say why. You can say yes, but you've got to be able to explain it.
Because you can at the halfway point.
Keep going.
At the where A, B, and where the radius and the two tangent points create a straight line.
Do they?
No.
They do not. In fact, Andreas,
Mhm.
they cannot. There is no way, because do you see what the tangent points, the tangent lines would
Yeah.
have to look like? The satellite would literally have to be, the length of the satellite would have to be the diameter of the Earth. The length of the satellite would have to be equal to the diameter of the Earth, because the only way to cover 50% of it, Andreas, would be to have a satellite that can create power, that can be from here to here. Does that make sense?
Mm-hmm.
And since satellites do not span 8,000 miles, you can never cover. So this angle, what can we conclude now, Andreas, about this central angle theta? So we can conclude that the measurement of angle ACB must be what?
Less than 180 degrees.
Oh my God, you are amazing, my friend. That is why I love working with you as a mathematician. That angle must be less than 180 degrees. And therefore, the coverage can never be. Now, it's interesting, Andreas. What if we say, do you think it costs a lot of money to send a satellite 22,000 miles into the atmosphere?
Yes.
What if we had a satellite that was maybe only 5,000 miles? What do you think the coverage would be? So I'm going to sort of simulate a much, a much less, smaller altitude. And I'm going to call that 5,000 miles. Well, actually, you know what? Let's do this. Let's call it 3,000 miles. All right. So this, instead of sending the satellite 22,000 miles, we're going to send the satellite only 3,000 miles up. You know that the radius is how much? Come on, you know that the radius of the Earth is how long? Real quickly, Andreas, I need it very quickly.
4,000.
4,000, and therefore CA is 4,000, and CB is 4,000.
Yeah.
Now, Andreas, what do we know about these triangles?
Right triangles, congruent triangles.
They're right triangles at angles what and angle what?
Angle CAS and angle CBS, and they're also congruent.
Oh my God, beautiful. Therefore, my friend, these little angles are congruent through Kappa Kataka. Now, what is the measurement of that angle? The measurement of angle ACS
in inverse
is equal to
cosine.
what? Oh,
Inverse cosine of 4/7.
you are fantastic. The inverse cosine of 4/7. And let's see if you can do that very quickly. On your calculator, go for it.
55.15.
So that's 55 0.15.
Mhm.
And what do you know now? Come on, that the measurement of angle what? AC what? Come on, the whole point of finding out that angle was so we could find out the what?
110.3
Is the what?
is the coverage.
No, 110.3 is just the what. You have to name it. I didn't even finish naming the angle because I wanted you to.
As angle
And take your hand away from your face so I can really hear you. ACB, because that's the central angle. And now,
and 30, it covers 30%.
why? How did you get that?
But I divided by 360.
And you got exactly 0.3?
No, it was, but the first two digits were 30.
So you got what?
30.
So point, and what, let's be a little bit more specific here. So 110.3 divided by 360 is 30 point what?
No, 0.3068.
Yeah, but I'm looking for a percent.
30%. 30.6%.
So the coverage, now this is amazing. The coverage of a satellite at 3,000 miles, 1/7 of the coverage of this satellite in our problem, 1/7, that covered 30% of the Earth's surface.
Mm-hmm.
Now, I think it's expensive to send satellites 22,000 miles away. So if we could cover 30% of the Earth, maybe we would only need 4 or 5 satellites to cover the entire Earth, whereas maybe we only need 3 at 22,000 miles. So it's a really important question, is to say, how do we use this information wisely? Now, the last thing I want to ask you is, what is the line of sight? The line of sight, which is segment SA or segment SB, the furthest distance that that satellite can see on planet Earth. How would you figure that out? We've only got a few minutes here, so what can you do? What theorem are you going to use? Do you remember how you find a missing side of a right triangle? What theorem are you going to use?
What is LOS?
Line of sight. Good question.
Line of sight on 26,000 squared divided by 4,000 minus 4,000 squared equals, and the square root of that.
Now say it all as one. Put your glass down there and say it all as one. So the line of sight will equal the what? The square root of
26,000 squared minus 4,000 squared.
So 26,000 squared. Let's see you do that on your calc right now.
Mm-hmm.
Minus 4,000 squared. You working on that?
I already did it.
And what do you get, my friend?
25,690.47. I rounded up to the nearest hundredth.
So amazing. So you just found out that the line of sight is slightly more than the circumference of the Earth. So it's a pretty amazing thing that you were able to do with simple trigonometry, right triangles, Pythagorean theorem and understanding how central angles and intercepted arcs work on a circle. So really exciting stuff. I'm really proud of you. I'm going to save this. I'm going to create a PDF for you.
Valerie's here.
And hi, Valerie. How you doing, kiddo?
Good.
You having a good night, I hope. And Andreas, let's call this the Andreas satellite coverage 3/22/20. And let's see, we're going to save this. And my friend, I will see you on Tuesday. Have some fun with trigonometry. And I hope you have a great evening. Take care, buddy.
I'll see you.
Good night.